Hello everyone, thanks for the introductions. Today I'm going to present our paper WaveEar, exploring a millimeter wave-based noise resistant speech sensing for voice user interfaces. So this is a joint work with my collaborators from SUNY Buffalo, Nanjing University of Posts and Telecommunications, and also UCLA. So recently, voice user interface or VUI are becoming more and more pervasive in our daily life. And this is because it can provide a more efficient and natural way to interact with our devices without any touching or typing. We can get navigations by our voices while driving, or do a touchless searching in Cookbook while cooking, or even get many files ready by only single voice command. So there are so many interesting and potential applications that voice user interface can bring to us. And that's why the related market size has reached 1.3 billion at last year. So let's record the history of the user interfaces. About 30 years ago, the Bash was released. It brought us the command line user interface. And now most of the Bashes are running on the Linux servers. And about 18 years ago, the Mac OS was released. And it brought us the graphical user interfaces. And now we are experiencing the rising of the voice user interfaces. So here we want to ask a question: is voice user interface ready to replace the graphical user interface and fulfill the increasing demands of the pervasive interactions? The answer is no. The current voice user interface is not ready. You can think about it. Would you do any voice-based interactions with your device like Google Assistant or Siri in a noisy environment? The noise could be traffic noise, residential noise, or construction or crowd noises. So we won't do that because we know we will fail. It's a very common sense that the noise is the first and biggest barrier to acoustic-based voice user interface. So the voice community have put much efforts on the acoustic noise cancellation. Most of them are related to microphone array or the throat microphones. For the microphone array, it leverages multiple microphones to distinguish our voice from the complex environmental noises. So naturally, it will cost because it uses multiple microphones, and it also requires an active noise cancellation algorithm, which is extremely hard to design. As for the throat microphone can provide acceptable noise resistance, but it will also cause skin irritations and obstruct the daily activities. So is there any better solution for the modern and future voice user interfaces? So the new solution should be noise resistant for sure, because we don't want noise break into the system, and it also should be user friendly. It won't cause any inconvenience to the users, and we also want it to be more informative and low cost, so that the quality of the voice can be guaranteed, and also the devices could be cheap. So with those requirements in our mind, we propose the WaveEar, which is a brand new framework for the speech sensing. So this is a comparison between the traditional framework with the WaveEar. We could see that the traditional voice sensing framework is indirect because the voice of the user is propagated by the air vibration. And in the air vibrations, there are so many other kinds of the noises. And those composite air vibrations captured by the microphone and converted to the voice-related signal by the MEMS. And different from it, the WaveEar leverages the millimeter wave to directly capture the user vocal vibration and then an end-to-end mapping from the reflected millimeter wave to the voice of the user. So let's take a close look at the vocal vibration. Vocal vibration is defined as a near throat skin vibration that is caused by our speaking airflow and the movement of our articulatory organs. So we could see that it contains most of our speech information. And we also found that millimeter wave could provide enough resolution to capture our minute skin vibrations. In our initial study, we pointed the millimeter wave to the throat of the subjects and asked them to speak A, B, C, and D for 2 times. And we found that the reflected millimeter wave share a very similar envelope. And this indicates the feasibility of the WaveEar. So here's the general idea about how the WaveEar works. So WaveEar would point the millimeter wave to the throat of the user, and the vocal vibration of the throat would interfere the reflected millimeter wave, and thus encoding the speech information to the reflected millimeter wave. We extract the speech information contained in that millimeter wave and reconstruct it to the voice, and thus we can support speech sensing in multiple scenarios. So how is the millimeter wave generated? We designed and implemented a 3-board millimeter wave probe, which contains the baseband board, MCU board, and the radio frequency board. Technically, the operational amplifier can generate an analog sawtooth signal, and this signal can control a free-running voltage-controlled oscillator, which is on the radio frequency board, to generate the frequency modulated continuous millimeter wave, which is also called FMCW here. And our design can generate the 24 gigahertz FMCW wave, which is enough to capture the minute skin vibration of human beings. So of course, users want to use their voice at any location around the WaveEar, which means the interactions of the users and the WaveEar could happen at an unfixed position. So in this case, pointing the millimeter wave to the throat of the user is very important because the antenna gain would attenuate very quick in the side slope. And it will cause low signal-to-noise ratio and finally hurts the sensing quality. So how would we overcome this challenge? We use digital beamforming. So technically, the WaveEar would manipulate the millimeter wave probe to steer the beam in all directions, and then feed the reflected millimeter wave to the throat localization module. In this module, the decision tree would detect the throat according to the time and the frequency features of that signal. So with the throat localized, shall we start the transformation from the millimeter wave to the voice wave in the time domain? The answer is no, because the important frequency domain speech information is implicit and it's very hard to extract. So we augment those implicit time frequency features and informations by the spectrogram. Spectrogram is a visual presentation of a signal with it varies with time, and it presents more correlations and patterns such as formants and sound intensity, which are very important to we humans to understand the voice. So the next step is learn the voice spectrogram from the millimeter wave spectrogram. We could see that the learning is very hard because first it requires to change large part of the spectrum to appear coherently, and the second, the minute changes in the millimeter wave spectrogram are related to a huge differences in the spectrogram of the voice. So here we propose the WaveVoiceNet to terminate this challenge. The WaveVoiceNet is based on an encoder and a decoder architecture, and the encoder would exhaustively extract the vocal vibration information, and the decoder decodes those important informations to voice spectrogram. Note that here the residual blocks could make the encoder more deeper, so that the long-term and the short-term speech information could be extracted. And finally, we use Griffin and the LIM algorithm to reconstruct the voice of the user from the spectrogram. So then we evaluate the WaveEar. In the experimental setup, we implemented the customized mmWave FMCW probe. And we also implemented the WaveVoiceNet by PyTorch and trained it on 3 GPUs. And about the participants, there are totally 21 subjects that were involved in our experiments, and 11 of them are males, and the rest are females. Their ages are from 21 to 35. So they are asked to read 5 materials listed here. That includes all the phonemes in English, and finally we got totally more than 40,000 examples for training and testing. So how is the WaveEar? Demo is worth 1,000 words.
WaveEar, exploring a mmWave-based noise-resistant speech sensing for voice user interface. WaveEar setup. This demo compares WaveEar with microphone in quiet and noisy environments.
International Conference on Mobile Systems, Applications and Services is awesome. International Conference on Mobile Systems, Applications and Services is awesome. Can you hear me in the noise? Can you hear me in the noise?
Okay, so now we all know that the WaveEar could help the speech-to-text system to hear in a noisy environment. But the first question we will still ask is, how accurate is the reconstructed voice? So here the matrix is MCD, which is male septural distortion. So it is a physical acoustically motivated measurement, which means it can take the human acoustic system preference into consideration. To calculate the MCD, we compare the reconstructed voice with ground truth in the male septural domain, and calculate the mean square error pixel by pixel. And we compare the MCD of the WaveEar to that of the microphone in a quiet environment, and 21 subjects speak in front of the mmWave probe, and we could see that the average MCD of the WaveEar is very close to the set of the microphone. So this indicates the WaveEar could reconstruct a clear and high fidelity voice in a quiet environment. So how about a noisy environment? We do experiment with the same setup, but in more noisy environments. The first interference is pop music, like what we heard just now. And the left sides are the spectrogram of the WaveEar, and the right side is the one that comes from the sound of the microphone recorded sound. And we could see that the interference caused by the pop music includes the instrumental beats and the harmonic, and both the two parts cannot break into the spectrum of the WaveEar. And the second one is the presentation interference. We can see that the echo and the presentation sound can also not break into the WaveEar. And the last one is the water flow sound. We choose the water flow sound is because it is very common in our daily life, and it is very close. It is very close to our voice in the spectrogram. So it has a very similar property of our voice. Sorry. So we can see that the water flow can also not break into the WaveEar. This indicates the robustness to the noise of the WaveEar. And a very important question we would ask is if I interact with the WaveEar while I'm doing other tasks like driving, will WaveEar still works? So we conduct the robustness analysis. Our analysis is two parts. The first part studies the impact of body motion, and the other one studies the impact of sensing distance and orientation. In the body motion part, we see that compared with the MCD, when the subject is steady, the small body motion like calling, typing, driving, or rhythm would not increase much MCD. This indicates that WaveEar is robust to the small body motions. And also in the impact of the distance and orientation, we could see that the WaveEar performs well within the sensing distance at 1.5 meters and the sensing orientation of 90 degrees. We also test the WaveEar using the speech-to-text system and report the word error rate here. We could say that the word error rate is steady within the distance of 1.5 meter and the orientation of 90 degrees. So this indicates sensing distance and orientation won't cause much decreasement of the performance of the WaveEar. So this is our exploratory study, and of course there are more issues to discuss. The first one is attenuation. We all know that the high frequency millimeter wave attenuates rapidly. So the key technology to solve this problem is to introduce advanced noise cancellation approach, so that the sensing quality could be improved. And the second one is authentication. So WaveEar could introduce a more secure and noise-resistant way to do the voice authentication. And the third one is environmental independence, because WaveEar is trained on unlimited environments. If we want to apply it to various environments, so the domain adversarial training would be helped. The last one is about human factor distortion. So we could use signal alignment to mitigate large body motion interference, and the vocal vibration or other body area needs further investigation. So let me summarize our paper. We propose an end-to-end non-contact and noise-resistant vocal sensing system, and we also we designed and implemented an FMCW-based millimeter wave probe and the corresponding throat localization algorithm. And we propose WaveEar, an end-to-end transformation from millimeter wave to the voice. And finally, we conducted experiments to evaluate noise resistance and robustness to other influences. That's all my presentation. Thanks for your attendance.